Hello, good morning everybody. So, we were discussing reaction dynamics. Now, last lecture we started to discuss this crossed beam experiment, and in that case we also talked about this angular distribution of products. Okay. So, and in that case two cross beams are used like this, and your detector is placed somewhere over here, maybe this way, so that it can detect the flux of particles that is coming out of the reaction, that is coming out of collision. So, now this is a typical schematic of a beam experiment, that where you see that this is a beam source. Okay. Beam source, it is basically a single beam. So, maybe you can put another beam this way, maybe at an angle of 90 degree this way, and you can introduce the second beam, second molecule in the collision chamber. Okay. So, that will make the crossed beam arrangement. Now, this is a beam source where you generate gaseous molecules, and that may be like something like supersonic nozzle, or maybe just the molecule is coming out due to diffusion. Okay. In that case pressure difference is less, but for supersonic jet the pressure difference is very high, and in that case you need to introduce carrier gas, but for the other case you may select by using a chopper. Okay. And here this beam source, then it is the collimator. If it is a charged material, I mean charged entities or charged gaseous molecules, then you may put some electric field. Okay. Put some electric field that will collimate it. Okay. That is collimate means you can select your area through which it is passing. You can make it narrower, you can make it bigger. And then there is a beam shutter that sometimes it allows the beam to pass through, or sometimes it does not allow. So, that is why you have to have a shutter. You have got a collision chamber. Okay. For the collision process to take place, you need to have a collision chamber, and then this is the outgoing side, that is the molecules or the mixture of products and reactants, unconverted reactant, that will go this way, and you have got a detector which detects the flux of particles. Okay. So, it is a collision chamber, it is typically a gas phase reaction. Okay. And now the question is, we started to have our discussion based on collision theory. Now, why it is so, means why collision process is taken into account in order to understand this chemical reaction dynamics, that is molecular reaction dynamics. Okay. Now, collision theory is the elementary theory, I mean the basic theory, which deals with deals with the chemical reaction rates. Okay. And it is thought to be the reason, that is the collision is thought to be the reason for chemical transformation to take place. Okay. So, if there is no collision, then there is no chance of this exchange of atom from one center to another center. Okay. So, that is why collision is very important, and collision is basically a scattering event. Okay, that is why scattering theory has been introduced over here to understand the dynamics, to understand the chemical reactivity and how to control chemical reactivity. So, these are the involved associated questions, okay. And therefore, we tend to treat the chemical reaction in the framework of scattering theory. Okay. Now, next question is molecules, atoms. These are all quantum systems. That is associated with quantized energy levels, Next question, why then, if these molecules, that is the interacting entities, are quantum system, then why should we use classical theory? Why not directly quantum theory applied to such cases? Okay. Okay, why classical model? Then question is, why classical model? Why classical model? Now, the essential physical concepts are much easier to understand in classical picture, and classical scattering models are still used even for moderately sized molecules or smaller molecule having atoms maybe greater than 2-3, and in that case quantum chemical calculations, quantum chemical simulations are very much expensive. It is time consuming and it is very much expensive. Okay. So, that is why classical model can explain many things nicely. So, that is why classical model is introduced. Okay. And I already have talked about this types of scattering event. Okay. One is elastic scattering, another is inelastic scattering, and third one is reactive scattering. Now, for elastic scattering, total kinetic energy of the initial state of collision partners are conserved. I mean, before and after collision it is conserved. Inelastic scattering, so the kinetic energy is transferred to the internal states of the reaction partners, but in that case chemical structure is conserved. Maybe if the kinetic energy is converted to some vibrational degrees of freedom, maybe you will generate vibrationally excited molecules. Okay. So, that is why it is not although it is inelastic scattering, but it does not lead to any restructuring of atoms within the molecule. The third one is reactive scattering. Okay. In that case kinetic energy, internal energy states and chemical structure all are changed. Okay. So, I mean in that case redistribution of atom may be A plus B C giving rise to A B plus C. So, you see that it is restructure, chemical structure is modified. Okay. So, that is called the this reactive scattering. Okay. Now, when it is the question of crossed beam experiment, that is to find out the flux that is the angular distribution. Okay. So, in that case you have two beams this way, another one this way, another this way. Okay. Okay. So, this is your say BC, and this is your say A, and your detector is placed, detector is here, and it will change its orientation. The data which is obtained from the detector is basically your obtained in laboratory frame. Okay. So, laboratory frame means like this, this is your A, this is your BC, and this is the theta, the angle of the detector, that is the angle with respect to maybe BC or maybe with respect to A. Okay. Let us say it is the angle with respect to BC, and scattered species is detected over here. Okay. So, you see this is A, this is B, like A plus BC, this is the scattered species, and these are in laboratory frame of reference. So, you have to convert to the center of mass system, because in this case it is more important to talk in terms of the relative motions rather than with reference to a laboratory frame. That is why in order and the data is plotted, that is the scattered species, the signal for the scattered species is plotted, I mean the flux of the scattered species is plotted in reference to your center of mass system. Okay. Now, for collision between molecules, the relevant kinematics are defined by their motion relative to one another. So, collision between molecules, collision between molecules, the kinematics, the relevant kinematics defined with respect to relative motion relative motion with respect to one with respect to another, and not by their absolute motion, and not with respect to the absolute motion in laboratory frame. So, that is most important. Therefore, we need to have a transformation of the laboratory axis system. We need to have a transformation of the laboratory axis system to the center of mass coordinate, like this. This is laboratory system, this is center of mass system. So, in that case, transformation, as I told in my last lecture, that whenever you do for a cross beam experiment, you get the detected signal, okay, and then you have to convert it into the center of mass system. So, how to do that? Okay. So, this is our center of mass, this is A, this is B. Okay. So, this is R A vector, okay. This radius vector of A, radius vector of B, this is the origin, and this is the radius vector corresponding to the center of mass. Okay. Now, R C, this vector is equal to M A R A plus M B R B divided by M A plus M B. Okay. So, this is with respect to this is the R C, that is coordinate vector of the center of mass. Okay. This corresponds to the coordinate vector, and the relative coordinate vector R is the relative coordinate vector is R A minus R B. It is the relative coordinate vector, and this is the center of mass coordinate vector, CM coordinate vector. Okay. And from vector principle, it can be easily shown that the kinetic energy, E kinetic energy for this system, E kinetic, that is the kinetic energy of the system, can be written like this: half ma Va square plus half mb Vb square is equal to half mv square plus half mu v square. Okay, where Vi is equal to Ri this vector dot, V is equal to R C vector dot, and V is equal to R vector dot. This way you can write, and M is caps M is equal to Ma plus Mb, and this reduced mass mu is equal to Ma Mb divided by Ma plus Mb. Okay. So, this is the reduced mass. So, this way you can transform. So, this transformation is very important. So, you have to transform into the new coordinate, I mean this is your center of mass coordinate. So, therefore, you need to transform this, means using this concept you have to transform data from the laboratory frame to the center of mass frame. Okay. So, this is the transformation, that is transformation. Okay. So, you have to transform using this concept. Okay. And we talked about this means differential cross section. Differential cross section means it is your d sigma d omega is the differential cross section, and that you can, and I already have told the expression for sigma, and if these reactants are not oriented, then it should not depend on the phi angle, only it will depend on theta angle. Okay. Now, next for elastic scattering, as there are three types of scattering, of which one is elastic scattering. Okay. In that case, collisions happen and kinetic energy is conserved. Okay. And it is the simplest collisions, then kinetic energy conserved, and is the simplest scattering event. Okay. Let us see we would like to look into the collision trajectory. Collision trajectory of two structureless particles. that is they undergo collision. Okay. And total angular momentum is also conserved. Two coordinates are there. I mean, two coordinates suffice to describe the relative motion of the collision partners, and in that case one is the relative position vector. In that case we need two coordinates, one is relative position coordinate, and orientation angle. That is psi. Okay, and that is with respect to the original vector, original velocity vector, with respect to the original velocity vector. Okay, so let us see what is that. So you see here, this is the impact parameter and this is the trajectory. Okay, this is the trajectory. You see, just look into the mouse. Okay, and this is the collision trajectory, initial velocity vector, and there is a dip over here. This is the relative position vector with respect to the origin, and this r0 is the vector for the closest approach. Okay, psi 0 is the angle at the midpoint with respect to this initial velocity vector. Psi is the orientation angle, that is this vector, the angle that this r vector is making with respect to the initial velocity vector. B is the impact parameter, and this is the deflection angle. Okay, that is the angle that is made by the initial vector and the final vector, this final vector. This is the angle. So this is the amount of deflection that has happened. So if there is no collision or something, then the particles should have adopted this dotted line along this. Okay, now what does this mean? Let us try to see. So this means that it is the collision trajectory of the center of mass system. Okay, and this solid curve represents a trajectory with initial velocity v, okay, and the impact parameter b, and this is the relative separation r, which is a function of t, uniquely defined in terms of distance r, and the orientation angle, it also depends on the orientation angle psi. The trajectory is, you see, this trajectory is symmetric about this symmetric at this point. Okay, symmetric about the at this point here. Okay, and this is the distance of closest approach r0. Okay, the final deflection angle is this. Okay, now in this case, if there is no potential, means there is no attractive potential. No potential is acting between the interacting particles, then it should have followed this dotted line. Okay, that is dashed line. If there is no interaction potential, the trajectory is identical to that traced by a particle of mass mu, that is a reduced mass, deflected by a potential Vr. It is a potential which is at at the origin, if you put a potential at the origin, and this, if it is like VR, if you put a VR potential as a function of r about the origin, at the origin, then this particle of mass mu should have experienced some force, and as a result of which there is a change in path with respect to your dotted line. Okay. In this case, we can imagine the trajectory as the trajectory of a projectile of mass mu, and which is seen by the observer, okay, which is who is placed on, who is located on B. Okay. So, this is a representation of the collision trajectory. Okay. Let us look into the conservation of the physical quantities. As I told that conservation is there. So, let us look into that conservation of physical quantities. Conservation of angular momentum, So, please refer to this figure here. Now, angular momentum is represented by angular momentum which is L is equal to mu v cross r. Okay. So, before collision, L before collision, angular momentum L, okay, before collision is equal to L after collision. After collision. Okay. So, mod L is equal to L, which is equal to mu v cross r, and in this case v is the initial velocity vector. Okay. It is the initial velocity vector, okay, which is mu v dot r sin psi. Okay. Now, this is one expression. This you can write L in this way. Therefore, and what is B? B is basically r sin psi. R sin psi means you can replace this r sin psi with impact parameter, and so you can relate this with impact parameter. Parameter B. So, ultimately L is equal to L, which is equal to mu v into B. Now, what about total energy of the system? In the same way, for the physical quantities, what about the total energy of the system? Total energy is the means if you recall such type of system where there is like potential energy is having this type of form. Okay. So if you consult a standard classical mechanics textbook, then you will be finding that E will have 3 components. Okay. E kinetic plus E potential plus E centrifugal. Okay, that is why the term centrifugal barrier has been introduced. Okay. Centrifugal barrier, because a barrier is phased and which looks like as if a centrifugal force is operative. Okay. So, for a say 2 particle case, if you plot the potential energy, I mean total energy of the system, then it will have these parts. Okay. And you can write each component in this way, that half m r square, like mu r dot square, okay, plus v r plus half mu r square psi dot square. Okay. Now, psi is, you know, the angular velocity omega. Psi is the angular velocity omega. Psi is the angular velocity. Velocity omega. Okay, so psi is basically psi dot is basically d dt. Psi dot is angular velocity d dt of psi, which is called the angular velocity. Okay, so that means this how this orientation is changing, this angular velocity, as a result of that this is changing. So, you have got this one, so this r is changing, therefore, this psi is also changing. So, this is your psi, this is changing, this angle is changing with respect to this, therefore, with time psi is changing, that is why d psi dt is used, okay, which is equal to omega, the angular velocity. Okay. So, you know, basically you can write from this half mu r dot square half m r square plus v r plus half L square by mu r square, L square by mu r square. Okay. So, that means your total energy is equal to half mu r dot square plus half L square mu r square plus V r. This part is the corrected potential, or it is called the effective potential. It is like it is the normal potential plus the, as a result of the centrifugal force. So, it is called the centrifugally corrected effective potential. Okay. Okay. So, so this is the centrifugally corrected potential. Now, centrifugally corrected potential is, you know, it is the centrifugal energy, that is energy taken up in the rotation of the position vector. Okay. So, that is why a centrifugal force is coming into action. So, therefore, this vector is changing. So, when it is here, your angle was different. When it is coming, this vector, position vector is changing its angle. Okay. So, this collisional angular momentum L is equal to angular momentum associated with the rotation of r about the psi. The effective potential of the collision contains both, that is the interaction potential, as I told, that is the interaction potential, and the centrifugal energy, that is because of this movement, it is changing. So, that is why effective potential term has been introduced over here. Okay, because you see again, if you see like this, that this is changing, this length is changing because it is as it is coming this way. So, your this vector, you see what is happening, that this is your starting vector, it is changing its position, this angle is changing this way. This tip, think of this tip, when the particle is here, that is mu particle, this particle of mass m, when it is moving this way, this vector, this relative position vector, the tip will do like this. So, therefore, your this vector will move this way. So, additional rotation. Okay. So, angular momentum associated with the rotation of r. Okay. Therefore, if you add up this energy contribution to the total energy of the system, then your potential is now become potential, normal potential, normal potential plus, okay, I mean normal potential means it is the interaction potential means may be attractive, may be repulsive. Okay. So, interaction potential plus this centrifugal potential, I mean centrifugal, this energy contains this centrifugal energy because of this rotation of the r vector, and of course the interaction energy. Okay. So, that is why it is called the corrected or effective potential. So, you are advised to go through any standard classical mechanics textbook like Harvard Goldstein, each year Harvard Goldstein, where you will be finding a detailed account of this process, how this I mean this centrifugal energy is coming, centrifugal potential that adds up to your interaction potential, giving rise to corrected or the effective potential or centrifugally corrected potential. Okay. So, next, as I already told that like intensity of the scattered molecule, okay, at a solid angle omega, that is the how to calculate that intensity of the scattered molecule or the flux of the scattered molecules at an angle I, say omega. The flux of molecule associated, I mean flux of molecules scattered into the solid angle omega. Okay. So, in that case this is related to your differential cross section, I mean differential cross section in relation to differential cross section d sigma d omega. Okay. Now, what is this I omega, which is d sigma d omega, which is equal to scattered flux per unit solid angle divided by incident flux of molecules per unit area, divide the incident flux, of molecules per unit area. Okay, and this cross section can be as already told you, that cross section sigma can be written as integral, because it's an you have to average it out. Okay, you have to average it out for different you have to total integral cross section, you have to find it in terms of the total angle. So that's why cross section means total cross section can be calculated by d sigma d omega, and this is your twice pi integral 0 to pi d sigma d omega sin theta d theta, where d omega is nothing but 2 pi sin theta d theta. This way you can find out. Okay. That's about this experimentally how to observe, because this way. And what is the experimental arrangement? That this is your mu, I mean mu mass, this so it is VR, and okay, you have got your, this is your d omega, okay, and this area I am making it a strip like thing. Okay, this is also a strip. Okay, so this is your 2 pi sin theta d theta, and this is your 2 pi b dB. Okay, and this is your angle theta, maybe in laboratory frame. So you have to have your detector over here. I mean, you have to detect in solid angle d omega. Okay. Next, calculating the differential cross section. Okay, how to how to do the differential, I mean how to calculate the differential cross section. And in this case, for simplicity, so calculation of differential cross section, calculation of differential cross section. Okay. So in that case, the reaction probability function, or maybe the opacity function, let us take this opacity function Pb to be unity, and in this case, if this is 1, then differential cross section can be written as, if this is 1, d sigma is equal to 2 pi b dB. Okay, you can check it, it can be written in this way. And again, because of scattering problem, since the scattering problem is of cylindrical symmetry, the solid angle element d omega can be written as twice pi sin theta d theta. Therefore, this is because of solid angle and cylindrical symmetry. So, assuming say scattering to be cylindrical, I mean cylindrical symmetry, symmetry, cylindrical symmetry, and the solid angle element, angle element will be that is d omega will be written as this. So, therefore, differential cross section d omega, I mean d sigma d omega, which is equal to I theta, can be written as twice pi b dB divided by twice pi sin theta d theta. Okay. Twice pi sin theta d theta. So just recall this this previous diagram. You should be able to do it, this diagram. Look into this diagram, you should be able to get some idea. Okay, so I theta, okay, that is differential cross section, which is this. Therefore, 2 pi gets cancelled. So, b dB divided by sin theta d theta. Okay. Therefore, it is your b by d theta dB sin theta. Okay. So, therefore, differential cross section has got relation with b. Of course, here in this case, for simplicity, your opacity function has been taken to be close to unity, or it is unity. Therefore, it depends on b, okay, and impact parameter b, of course, sin theta and d theta dB, that is variation of theta with b, that is this factor. Okay. Now, the next question is the value may not be, value of b may not be unique, I mean unique value, maybe more than one value of b, may can contribute, okay, in to the same, I mean more than one value of b may be relevant for the same scattering angle. Okay. So, in that case, what we have to do? That in that case, we need to take the summation. Okay, you need to take the summation. So, summation to get the overall contribution. Overall contribution means contribution from different impact parameters. Means same scattering angle, but maybe that same scattering angle could be due to different b values. So, in that case, we have to you have to take that into account as well. Okay. So, therefore, we need to sum over those things. So, therefore, the dependence, that is differential cross section, finally comes out to be, so differential cross section can be written as d sigma d omega, which is equal to I theta, which is equal to sum over b then by d theta dB into sin theta. Okay. So, d theta dB into sin theta. So, several interesting aspects may be obtained from here. okay, more than one. That is, in one case, suppose you have got two things, that is differential cross section, you see that it depends on B, but in the denominator you have d theta dB and sin theta. So what is happening that this differential cross section will have singularities. So, singularities that is d sigma d omega will tend to infinity, as in one case either this or that becomes 0, that is tends to infinity for number 1 d theta dB tends to 0, or number 2 sin theta tends to 0. Okay. Sin theta tends to 0 means one situation, and d theta dB tends to 0 means another situation. So, these are the two possibility, I mean two extreme situations that one might might be looked, we might look into. So, singularities. Therefore, we have got two situations. So, we will take this up in the next lecture. We are not going to elaborate into that. Before that, we have a quick look. We have started with crossed beam, crossed beam experiment, and then we told that this classical scattering is important, because quantum mechanical calculations, although they are accurate because these are quantum systems, but for 3 or more than 3 atomic system, it is very difficult, it is very time consuming, and it is costly, it becomes costly in that sense. So, that is why we take up this classical thing, and for your 2 beam experiment, you have to convert from the laboratory frame to center of mass system, and that we have discussed how to do that. And then we talked about this kinematics, how to do this transformation. Then we talked about elastic scattering, and given the we discussed this figure also, that is the scattering diagram, collision trajectory, how the path that it is following. Then we talked about this conservation of various physical quantities. Okay. Then how this idea of centrifugally corrected potential, and finally we talked about this calculation of the differential cross section, and how 2 situations can be obtained. So, like when d theta dB is 0 or maybe sin theta equal to 0, then 2 singularities may be obtained. So, these will be taken up in the next piece of lecture. So, till then, thank you.